And I'm going to share my slides now. And you guys can let me know if you are able to see the slides or not. So I hope that everybody is able to see my slides. Let's see here. Yes. Okay. Excellent. Let's get started. So today we are going to continue our discussion on matrices and how to solve a system of linear equations. We'll focus on sections 1.6 and 1.7 of the text. We'll be dealing with properties of matrix operations. And then we'll talk about a very important topic in linear independence. So we started talking about matrix multiplication in the previous class, and we sort of touched on this topic, but let me talk about a few cases on this slide. So the question here is matrix multiplication commutative or not, which essentially means does the order of multiplication matter? The short answer to that is yes, the order matters a lot. You cannot reverse the operation. So in general, matrix multiplication is not commutative, which means that if you multiply A then B, it is not going to be the same in general as B times A. Even though algebraic multiplication is commutative, matrix multiplication is not commutative. So let's take a look at a few cases. So in the first case here, we have an example where we are multiplying two matrices. A is a matrix of size 2 by 3, so it has 2 rows and 3 columns. B is 3 by 3. So when you're trying to multiply A and B, because we have a match in the columns of A and the rows of B, you will be able to multiply A times B, and the result of that will simply be of size 2 rows and 3 columns. So you get AB as 2 by 3. However, if you try to multiply B times A, we are not going to be able to do that. B times A doesn't exist here because the columns of B do not match with the rows of A. So BA is not defined in this case. Now let's take a case where even if both products are defined, even if the sizes match up, there might be different sizes at the end after you multiply. So for example, here we are taking A to be 2 by 3, B to be 3 by 2. So if you multiply A times B, we can do this quickly. This matches with that, which means that the result is going to be 2 by 2. So AB is 2 by 2. However, if you reverse that multiplication, if you wanted to do B times A, then we have a case where we need to check, do the columns of B match with the rows of A? And in this case, they do. However, when you multiply them, the result will be 3 by 3, right? So even though the sizes of each of those matrices are such that AB is defined, BA is defined, but the result of that are different sizes, which sort of validates this statement: matrix multiplication is not commutative. Now let's take a look at the third case here, where even the sizes of the result match up. So even if both matrices are square and of the same size, you may have AB doesn't equal BA. So in this case, we have a 2 by 2 matrix in A. Let me write this down here. 2 by 2 matrix in A and a 2 by 2 square matrix in B. So clearly everything is 2, so the sizes will match up. Let's try to see what happens when you do A times B, right? So if you do A times B, then you're going to get, the first entry will be this row, this column, right? So that'll give you row 1, column 1 entry of AB, which is simply going to be -1 plus 4. So you get 3 there. And then first row, second column will give you the row 1, column 2 entry in the product. So 1 times 0 plus 2 times 1 will simply be 2. And then for the second row elements, you get -3 plus 8. And then 0 plus 4, right? So when you do A times B, you get a 2 by 2 matrix whose elements are 3, 2, 5, and 4. But if you do B times A, let's try to see what happens here. And in this case, what you're doing is you're reversing it, right? So the first entry is computed by taking first row of B and multiplying it with the first column of A to get the row 1, column 1 entry in B times A. So in this case, what are you going to get? You're going to get -1 plus 0. And right away, just by looking at the first entry, you know that they are not matching up. AB doesn't equal BA. So you can still go ahead and complete the whole thing. Row 1, column 2 will give us -2 plus 0, -2. And then we are going to move to the second row here. So second row, column 1 will give us what? 2 times 1 plus 1 times 3. So that's 5. And then 4 plus 4, 8, right? And you can clearly see that even though they existed, the results were of the same size, still AB doesn't equal BA, right? So in general, we can say that matrix multiplication is not commutative. So let me just highlight that over here, not commutative. Okay, let's move on here. Now this slide just lays out all the matrix operations as rules, as laws. And we are, in order for matrix operations to be carried out, we are going to have to make sure that the sizes of the matrices are such that the results are defined. So we are, for describing these laws, we have 3 matrices that we are considering, A, B, and C. And we are also using 2 scalars, small a and small b. And we are assuming, and this is important, we are assuming that all the operations, whether it is matrix addition, subtraction, multiplication, and whatnot, all of these things can be performed, which means that the sizes of the matrices are appropriate for the matrix arithmetic to be valid. So we are making that assumption. What are some of the rules here? Matrix addition is commutative. So the order in which you add matrices doesn't matter. A plus B equals B plus A. Because essentially what you're doing is you're adding each element in each location. So that will satisfy because addition is commutative. How about associative law for addition? If you do add B plus C first and then add A, matrix A, it is going to be the same as adding matrices A and B first and then adding C. And it is the proof of this would still be valid because of addition being commutative. Next, we have we multiply matrices B and C first and then multiply with A, and the law says it is going to be the same as doing a matrix multiplication between A and B and then doing a matrix multiplication of the result with C. So this is associative law for multiplication, and clearly for this we have to make sure that the sizes are appropriate, and we are assuming that, so we are okay. We are going to deal with this in a little bit in more detail as well. So that's associative property. Next, distributive law. Can you distribute matrices if you have B plus C? You're doing the matrix addition first and then multiplying with A times that result. The distributive law says that is going to be equal to matrix multiplication of AB, matrix of multiplication of AC, and then adding those two. And then the order also you can swap. You can add B and C first and then do a matrix multiplication with A is going to result in BA plus CA. So distributive law again. But with this, you are adding here as your second matrix. Over here, you are adding first. So those are valid matrix operations. Next, we are replacing the additions over here with subtraction. And again, subtraction, because you're doing B minus C, the subtraction is going, you cannot reverse that. Subtraction is not commutative, so you cannot reverse the order here. But if you did this distributive law, it will satisfy. So for example, if you have a matrix A multiplied, matrix multiplication with B minus C, it's going to equal AB minus AC. So two matrix multiplication operations followed by a subtraction of the matrices, matrix elements. Next, B minus C multiplied by A, which is BA minus CA. So all of these are sort of distributive laws. The first two are for addition, the next two are for subtraction. Now let's include some scalars here. You have a scalar A here, which is getting multiplied with the sum of these two matrices. And in this case, you are multiplying the scalar with B first, you are multiplying the scalar with C first, and then adding them up. So this is essentially going to scale your entries in matrix B, scale your entries in matrix C, and then you're adding them up, which should be the same as adding the elements up and then scaling all those entries with scalar A. Similarly, for subtraction, this will also be okay. So B minus C scaled by A is going to be AB minus AC. Small a is referring to a scalar here. Next, more properties on this side. Has some matrices, has some scalars. If you have two scalars A and B multiplied by C, this is going to be AC plus BC. So it's kind of like distribution, but now you have scalars. And it's pretty easy to see why this would work. Here, what are you doing? You are scaling each element in C by A. Here, you are scaling each element by B. And then you are adding them up, which is going to be the same as adding the scalars up and then multiplying each element by in C by that added scalar. So say 2 and 3, right? So you can do 2 times C plus 3 times C, and if you add them up, it's going to give you the same as 5 times C. So it'll be okay. Next, A minus B, AC minus BC, small a and B are scalars. Next, what about those scalars getting multiplied? AB times C is going to be A, BC. So here you are essentially multiplying each value. When you're doing scalar multiplication, all you're doing is you're multiplying each entry in the matrix C by B or by AB. So it doesn't matter the order. It's just one matrix here. Next, AB followed by C. That is going to be the same as doing a matrix multiplication of B and C and then multiplying it with each element in the product by scalars A, or you could do B times A and C. Now we have to be careful here. This doesn't equal ACB, right? Like we cannot reverse the order in which we are doing the matrix multiplication. All we are changing is we are still doing B followed by C, B followed by C, B followed by C. We are just moving that scalar around, which we can do. All right, questions here? Just some laws, a lot of them, they're just algebraic theorems. We need to be a little bit careful when we are dealing with multiplication, matrix multiplication. And the key here is we have assumed that the matrix sizes are going to be okay for the arithmetic to be carried out. All right, let's try to see an example. Over here we are finding out ABC, right? So when you say what is the product of A, B, and C, right? Matrix multiplication of A, B, and C, what you can do is you can either do B and C first and then multiply with that A, or you can find AB product first and then multiply it with C. You can do one or the other, but both of that are going to equal ABC. So let's assume a few cases here. So we have matrix A assumed to be 1, 2, 3, and 4. Matrix B has 2 rows, 2 columns, -1, 2 are the first column, 0 and 1 are the second column. And then matrix C is 0, 3, 0, 2, 0, 1 for the 2 rows it has. Let's put down their sizes quickly. So 2 by 2 here, 2 by 2 here, and 2 by 2 rows, 3 columns here. Right. So hopefully we are doing this and the sizes will match up as we are doing the matrix multiplication. So let's try to do the first case. We are multiplying A and B first, and then we are finding the product with C. So AB is going to equal what? Let's put a couple of Let me use red here. So we have A times B. So A times B is going to be another 2 by 2 matrix, because this equals this. You will be able to do the matrix multiplication, and the answer will be the outer dimensions, 2 by 2, right? So 2 by 2 matrix. Let's try to find out what that is going to be in here. So that is A and B. Let's see, negative 1 plus 4, that's 3. 0 plus 2, that's 2. Negative 3 plus 8, 5, and 4, right? So that's A times B. And then we are going to multiply it with the C matrix. So C is going to be what? 0, 3, 0, 2, 0, 1. And again, this guy has the size 2 by 2, and this guy has the size 2 by 3. The inner dimensions do match, right? The inner dimensions match up. And the result of this is going to be 2 by 3, right? So the result of this should have 2 rows and 3 columns. Let's try to find those. Let's see, 4 for the first entry, 3 times 0 plus 2 times 2, and then I've got 9, and then I've got 2, and then I've got 8, and I've got 15, and then let's see, 4. So we've got a 2 by 3 matrix in AB first, then C. And this should clearly match up the next one. Let's try to prove that with this example here. Same matrices. So we are doing B and C first. Let's write down A. 1, 2, 3, 4. The order matters, so we are going to keep that order, followed by B and C. So let's do B and C. Can we do B and C? 2 multiplied by 2. All right, so inner dimensions match, and you're going to get something which has a size 2 by 3. So that's okay. Let's see. B, C. So 0 and 0. All right. And then we have got negative 3 plus 0. And then we have got 0, 0. And then we have got 0, 2. 6, 0. And then 1. And then when you, let's quickly write down sizes, 2 by 2, 2 by 3, inner dimensions match. The result is going to be the outer dimensions. Let's try to write that out here. So it's going to be 4. And then we have got negative 3 plus 12. And then we have got 0 plus 2. Then we have got 8. Then we have got negative 9 plus 24. All right. And then we have got 0 plus 4. And we can see that it is a 2 by 3 matrix, and we can see that this is equal to this. Right. So here we can write down this property here, which is, so you can say A, B, C equals A times BC first, or you can do AB first, then you can multiply with C. So we have sort of looked at that with this particular example of matrices. All right, questions about this? The order matters. Like once, twice, let's go. All right, let's talk about some special matrices here. The first matrix we are going to look at is a zero matrix. So a matrix whose entries are all 0 is called a zero matrix, and we are writing that as a bold 0, right? So the bold is going to indicate a vector. So we have a vector or a matrix here. So let's see, if we have a 0, you can have that equal to be 0, 0, 0, 0, 0, 0, or you can have that to be 0, 0, 0. All entries, no matter what the size is, should be all 0, right? So we have over here 3 rows, 2 columns, 1 row, 3 columns. They're all 0 matrices. 3 rows, 2 columns, and then 1 row, 3 columns. That's a zero matrix. All entries are zero. Now let's take a look at some properties that are relevant to a matrix along with a zero matrix. So let A be a matrix here. In all these laws, we are using A as a matrix. And again, we are going to make that same assumption that matrix sizes are such that the matrix arithmetic can be carried out, can be performed. And the answer is defined. So if that is the case, let's take a look at what happens when you add a zero matrix to A. So if you have a matrix A, and if you have the same size zero matrix 0 here, the result of that is going to be 0 plus A, which is simply A. Because all you're doing is you are adding a 0 to each element in matrix A, which is not going to change the value. Next, A minus A is going to give you the same zero vector or zero matrix depending on A. So can you guys tell me the size of this zero matrix here? What is going to be the size of this zero matrix here? Can I say that it should be the same size as A? Right? Yeah, right. Exactly. Same size as A. Because in order for me to do the subtraction, the sizes have to match up. And all I'm doing is I'm subtracting each element of A with itself. So I'll get zeros in all those locations. So the size is going to be the same as A here. Next, 0 minus A equals negative A, which is simply 0, 0. Each element is going to be a 0 here. That element is getting subtracted by each element in A. All we are doing is changing the sign of each element in that case, which is equivalent to multiplying each element by a scalar, which in this case is negative 1. Next, A times 0 is going to be 0. Why? Because you are taking A and you're multiplying with all zeros. So no matter what you have for matrix A, because you are multiplying with all zeros and adding those values up, you're going to end up with 0. Next, 0 times A equals 0. So you're taking all entries in 0. Or we just have to make sure that the sizes match up, right? So for example, let me take a look here. Let's consider this. Let's consider this particular law here. So we have 0 matrix multiplied by A. What can we say about the size of the matrix? So suppose A is m by n, right? So if A is m by n, let me write down the size here, m by n, m rows and columns. What can we say about the limitation on the zero matrix? What can we say about the... So in order for this to be carried out, what can I say about the columns in the zero matrix? What do they have to be? The columns of zero matrix here, m, right? So the inner dimensions have to match. So the columns in A have to match up the rows in, the columns in 0 have to match up the rows in A. So that should be m. But what about here? What can I have as the rows in the zero matrix? Anything. That's exactly right. So I can have anything over there, right? But that anything, right, that anything is going to dictate the size of this guy, the resulting zero matrix. So this should be anything, the same anything, but it'll have n columns here, right? So all we need to make sure is that these match up. And if they do, you can have any number of rows in 0, and the result will have that same number of rows here. So same here and here. All right, let's see. So these are zero matrices. Next, identity matrices. Very important matrix here, identity matrix. And the reason for them to be important is because each column in an identity matrix is a linearly independent set, right? So the columns of identity matrices are independent, which is why identity matrices are very important. And we'll take a look at identity matrix and their some of the properties here. So an identity matrix, first of all, it's a square matrix, which essentially means the number of rows and the number of columns in an identity matrix have to match up. Now, what happens in an identity matrix? All the diagonal elements in the identity matrix are a 1. And every off diagonal element is a 0. So I can write some examples here. Let us see. I can write an identity matrix of size 3, which I simply write as I3. I3 means it's an identity matrix with 3 rows and 3 columns. I just need to write 1 times 3 because it's a square matrix. So all the elements in the diagonal, the principal diagonal, are a 1. And all the other elements are a 0. So I've got a 0 here and I've got a 0, 0 there. All the other elements will be a 0. So this is a square matrix, clearly has the size 3 by 3, and I'm going to call that I3. And you can see why this is going to be linearly independent, right? The reason is column here, column here, column here. No matter how you scale column 1, you can never get column 2 or column 3 because of the location of zeros, right? So that's why these identity matrices are important. Next, let us try to look at how they are denoted. Denoted by the letter I, and with the subscript n, it denotes that it has n rows and n columns. The size would be n by n. Next, let's take a look at a theorem here where A is a matrix. It's not a square matrix. M rows, n columns. That's A. Then I identity matrix of size m, so m rows and m columns, times A is the same as A is the same as A times I sub n, which is essentially in algebra. You say if you multiply a number by a 1, you don't change its value, right? So that's sort of how this relates to arithmetic algebra. In linear algebra, we are talking about it in terms of identity matrices. So let's take a look here. So first of all, you see, if A is, say A is 2 by 3, right? So if A is 2 by 3, I'm going to need IM, right? I2A. That is going to be okay because I have 2 by 2 in this case and I have 2 by 3 in this case, and I will be able to multiply, right? Because the inner dimensions will match. The result of this will be 2 by 3, which is the same as A. At least in the sizes, you can see that it'll match up. But if you wanted the identity matrix on the right, the second matrix, then what do you need to do? You need to do I times I3, right? Because then this is 2 by 3, this is 3 by 3, inner dimensions match, and then the result will be 2 by 3, which is A, right? So I2 times A is the same as A is the same as A times I3. So that's what we are writing over here. Let's take a look at A times I3. Sorry, there's a square matrix here with A, and we are trying to do A times I. Let us see if this equals, this is a question mark A, right? Like, let's see if we get back A if you do this. In order for matrix multiplication to happen, I hope you guys agree that this should be I2, right? This should be selected as if it is I2 because 2 rows and 2 columns. We are going to need that to make sure that the multiplication can be carried out. So we have 2, 7, negative 1, 5 here. And then we have 1, 0, 0, 1 here. And if you multiply them, you are going to get 2 times 1 plus 7 times 0, 2, and 7, and negative 1, and 5. And you can check out the math here. You are going to get another 2 by 2 matrix, which essentially matches the same as A. And in this case, because A is square, you could have also done I2. You could have also done the same as, is going to be the same as doing I2 times A. You would have gotten the same result. Questions here? All right, let's go on here. The transpose of a matrix. So essentially we are changing the rows to the columns, columns to the rows, right? Like, so we are sort of flipping the matrix here with the transpose. So if A is any matrix of the size m by n, m rows and columns, then the transpose of A is denoted as A superscript T, cap T, that is A transpose, and it is defined as n rows, m columns. So we are essentially twisting, like turning the matrix 90 degrees, right? So where the first column is the first row of A, whose second column is the second row of A. So we are essentially making the first row into the first column, the second row into the second column, and so on, right? So if A matrix is here, it's a 2 by 3 matrix, right? So this is 2 rows, 3 columns. And how can you say about, what can you say about A transpose? The transpose is going to be, you see, the first, I flipped it here. The first row is what? 2, negative 4, 3. So that is going to become my first column. So this is going to be 2, negative 4, and 3. And the second column is going to be 5, 0, and negative 2. And the size of this is going to be 3 by 2, right? So we have n by m has become n by m. The number of rows and columns have switched because we have interchanged each row with each column. So the first row has become the first column, second row has become the second column. So that's a transpose. Now, because you did that, we can say this. The I comma jth element in the transpose of A is going to be exactly the same as j comma ith element in A. Let's try to validate that. Let's pick this guy, this 0, right? So let's pick this 0. What can we say about this guy, 0? Well, we can say that this is A transpose. It is an element into A transpose, and the size of the location of this guy is row by column, second row and second row and second column, right? 2 by 2. Maybe I choose a different one because this is 2 by 2. I'll choose a different one. I'll choose this guy. All right, let's take this guy. If you take this guy, this element, it's an element in A transpose, and the location of this guy is third row, second column, right? So instead of writing 3 by 2, I'll just write 3, 2, right? Like ij, 3, 2. Now that, before we did the transpose, where was that negative 2? It was right here. So this was the element in A, and the location of this was 2 by 3, 2, 3, right? You see that? So the same element now, if it was at 2, 3, location 2, 3, ij, now it has become ji in A transpose. So that's how we are able to write this guy. The I comma jth element in A transpose is the same as j comma ith element in A. A matrix is symmetric. It is called symmetric if the transpose of A is the same as A itself. Like if you do the transpose, then the matrix doesn't change. And we can quickly write an example here. Let's see. We can make, all we need to make is, say, this is 5, right? All we need to make is the other diagonal elements to be the same. So if I pick 3 here, I need to pick 3 here, and that's it. And you can see that if you sort of change the rows and columns, you are going to get the same thing, right? So first row becomes first column, 5, 3, so it'll remain 5, 3. 3, 4 become 3, 4. It is the same. So all we need is these two guys to match up, right? So that's an example of a symmetric matrix. It has to be such that A transpose equals A. All right. Questions here? All right, let's take a look at some more properties, and these are relevant to the transpose of a matrix. So some properties listing over here, and there are some interesting results, and we'll try to elaborate on that. So the theorem here is what? If the sizes of the matrix are such that the given operations can be performed. Again, the sizes of the matrix are important because we are doing some matrix arithmetic, and we are assuming that the sizes are going to be such that the matrix of arithmetic can be carried out and the answers are going to be defined. So if you do the A transpose, which means you have change the rows and columns, and then columns and rows back. You get back your original matrix. It's like the double transpose is canceling out. Next, A plus B, the transpose of the addition is the same as A transpose plus B transpose. K is a scalar. If you multiply the matrix A with a scalar K and then transpose, it is going to be the same as finding the transpose of A and then scaling each element in A transpose by that scalar K. This is different, and this is important. So let's try to look at this particular theorem, property here. If you do a matrix multiplication between AB and then take the transpose of that result, it is going to be the same as finding the transpose of B and then multiplying it with the transpose of A. So you're switching the order of A and B here. And in fact, you can actually scale that up. You can do A, B, C, D. The transpose of that is going to be the same as D transpose, C transpose, B transpose, A transpose, everything reversed. Now, the important question here is, why is this result true? And we can prove this in terms of sizes. You can prove this. Let's take a look at how do you prove this in terms of a size, right? So let's take a look at how would this work out if you have a size limitation. So let's see, if A was M by N and B matrix is N by R, right? Then I can do A, B transpose, and if I do B transpose and A transpose, okay, so here, so I'm assuming that A is M by N, B is N by R. If I did AB, what would be the size? What would be the size of AB? Can I say it's going to be M by R, outer dimensions? And then what about AB transpose? It is going to be reverse, R by M, right? Now, let's compare that with let's see here. What can we say about B transpose? B transpose, the size is going to be R by N. A transpose, the size is going to be N by M. So B transpose, A transpose is going to be okay. You can carry it out because the inner dimensions are matching up, and the result is going to be R by M. And this matches that. So at least in terms of size, right, this is what we can call this size verification, right? In terms of size, this property over here, we are able to make sense out of that. But let us try to look at a lot more detail, which the size is the same doesn't mean all the elements are the same. So let's try to take a look at each element, and we'll try to prove this in general. So I have a few statements written over here, but instead of reading through the statements, let's actually try to prove it out, right? So I'm going to try to prove that the property AB transpose is the same as B transpose multiplied by A transpose. So for this, I will start off with some matrix A, and I will say A is a matrix here of M rows and R columns, right? This is A, and it is, say, M rows. I will choose M columns. No, these are M rows, right? And sorry, M rows and R columns. And this is rows. So M rows and R columns. And for B, I will choose something different here. This is for B, and I'm choosing R by N. And if I multiply those two, and I can, come on, if I can multiply because the number of columns here match the number of rows here, I can multiply in that order, and I will get what? I will get AB which is going to have M rows and N columns, right? So that's the first case here. Now let's try to take a look at something else, the other case. That's what we can say about A times B, right? So let's take a look at the other one here, which is B transpose, then A transpose. All right, so let's try to do B transpose first. So B transpose, what can we say about B transpose? This is going to be R columns, N rows. So this was R by N, this becomes N by R because we transposed it. Next, A transpose. A transpose is going to be some, this was M by R, this becomes R by N, R here, M here, and you get what? The product is going to be B transpose, A transpose. And the inner dimensions match, so you're going to get N by M, right? Which is sort of the opposite of M by N because we didn't do the transpose here. We didn't do this operation here. All right. So given this, let's try to look at a specific element, right? So if I wanted to look at a specific element in AB matrix, let's try to look at some element here, some arbitrary element here, right? And let us say this element is in AB, and let us say that this is element I, j, ij, right? Can I say that that element ij is going to be the same as AB transpose ji? Can I say that? Because we have noted that earlier, right? So if you do the transpose of a matrix, then you switch the number of rows and columns, which also means that you switch the index of each element. So ij becomes ji. We have seen that with numbers 2 and 3 in the previous slide. Now, the question is, how do you get this element, AB, ij? Can I say that you get this element by doing a dot product of row I in this and column j in this, right? So this is going to be row I, and over here you get column j. So if you take the dot product of row I and column j, you get that particular entry, which is I comma j in AB, which is the same as j comma I in AB transpose. Now let's try to look at B transpose, A transpose. So let's try to look at another entry here. I will highlight this with blue. Let's say I have this entry here, and this is, say, just as an example, I'm picking B transpose, A transpose, and the element that I'm looking for is Ji, right? Jth row and ith column entry in B transpose, A transpose. How do you get that particular entry? Well, you are going to need row J, right? Row J in B transpose and column I in A transpose. So let me write those down. Row J in B transpose and column I in A transpose. So if you take the dot product of row I and column J, you get this particular entry in B transpose A transpose, which is Ji. You guys see that? Now let's try to see if what do we know about row I in A and column I in A transpose. What is the relationship between row I in A and column I in A transpose? Row I and column I, A and A transpose. All right, when you transpose a matrix, row 1 will become column 1, row 2 become column 2. So row I becomes column I. So row I in A should exactly be the same as column I in A transpose. And similarly, column J in B will be the same as row J in B transpose. This will match this. What that means is the entry over here, which is j comma ith entry in AB transpose, is exactly the same as j comma ith entry in B transpose and A transpose. So when you multiply these two matrices A and B and then take the transpose, the resulting matrix, the j comma ith entry in that answer is going to be exactly the same as j comma ith entry in the resulting matrix if you did the multiplication B transpose A transpose. These are exactly the same because they were obtained by doing a dot product of the same row and column, row I column J, which is the same as row J column I in their transpose versions. You guys see how we prove that? All right. Let's move on. Did we have any? All right. So all of those things are sort of captured over here. You can read it if you didn't sort of follow that along, but these are statements reflecting the same things that we wrote earlier. Okay, let's move on to the next slide here, which is linear independence, a very important topic. We have a set of vectors. S has a set of vectors. V1, V2, and so on up to Vr. So there are vectors in this particular set, and these vectors, then the vector equation for this is going to be k1, some k1 v1 plus some k2 v2, and so on up to kr vr. K1, K2, K3, so on up to kr are scalars, and this is a linear combination of all those vectors, right? So this is a linear combination of the vectors. Equals 0 gives us a vector equation. And if this vector equation has at least one solution, which is this vector equation has at least one solution. We know that trivial solution, which is all the k's are equal to 0. And if it is the only solution it has, then we call it a linearly independent set. So only one solution. Only one solution, which is the trivial solution. Only solution which is trivial. Essentially means no non-trivial solutions to this particular vector equation. So the only way you get a zero vector is all the k's have to be a 0. If that is the case, then we call this particular set of vectors a linearly independent set of vectors. Can you guys think of a matrix which has a linearly independent set of vectors? This is a special matrix we have seen before. Zero matrix, no, that so zero matrix is all 0, right? So they are all the same point. So it's kind of like, it doesn't matter whether it is linearly dependent or independent, they are all zeros. So even if it was non-zero, can you guys think of a matrix which has vectors which are linearly independent set? Here, think about it like this: 1 0 0 1. This is a matrix. It has two columns. This is column 1, and this could represent this vector v1. This is column 2. This could represent v2, right? So if this is v1 and this is v2, how do you get a 0 at the end? Like, if you wanted to do kv1 plus kv2, k1v1 plus k2v2, how do you get a 0? That 0 should be what? That should be 0 0, right? How do you get a 0 0? Which essentially means you have k1 1 0 plus k2 0 1, second one, should equal 0 0. How do you get that? Well, the only way you can get that is if k1 and k2 are zeros. You guys see that? That's the only way. Because there's no other way you can cancel out the ones, because you got a 0 on the right. So identity matrices have columns that are linearly independent set. So it should only have one solution. If it has more than one solution, in other words, if it has any non-trivial solutions, then it is called a linearly dependent set of vectors. Let's take a look at an example. Question so far? Like, is the background okay? How are we calling it linearly independent and linearly dependent? All right, we'll take a look at some examples to see, to learn more about linear independence. And if it's not linearly independent, then it is linearly dependent. So we have 3 vectors here. v1 is a vector, v2 is another vector, v3 is another vector, and they are all in R4, right? R4 space. So it's a 4-dimensional space. These vectors are in 4-dimensional space. So let's see if these are linearly independent or dependent. Well, if you want to check, then you are checking for something like this: k1 v1. Actually, let me do this. Let me write k1 and then v1. I will put a underscore under the v, underline v, to indicate that it is a vector. K1 is a scalar. So k1 v1 plus k2 v2 plus k3 v3, that's it, 3 of them, should equal 0 vector. Finding the k values might turn into a set of equations. Exactly. That's where we are going, Sunny. That's exactly right. So k1 v1 plus k2 v2 plus k3 v3 should equal the 0 vector. So if you are able to find any k1, k2, k3, so of course if this one is always going to be a solution, right? There's not a trivial solution. That will always be there. And the real question is it the only way you can do a linear combination of these 3 vectors to get a 0? Or is there any non-trivial, at least one solution? Now, we are going to need to solve a system of equations to find that out. But for this example, let me give you the answer. Let me give you the values of k1, k2, k3 that actually satisfy this, which are non-trivial. So if k1 is a 1, k2 is a 2, and k3 is a -1, then this actually gets satisfied. So v1 plus 2v2 minus v3 is actually a 0 vector, which essentially means the answer for this one is yes. I don't know if it is the only one or there are many, but I found at least one non-trivial solution which makes these vectors linearly dependent. You guys see that? So you can say v1 is dependent on v2 and v3. v2 is dependent on v1 and v3. v3 is dependent on v1 and v2 in this case. So all of them are dependent on the others. You guys see that? So this would be a linearly dependent set. If it has to be linearly independent, then you can only have one solution to this linear combination equation, vector equation, which is the trivial solution. That's the only way you can call it linearly independent set, like we did for columns in a identity matrix. Next. So of course, finding the k values is now going to be the next task, right? Like, how do we find them? How do we find those k1, k2, k3 values for a given set of vectors? So let's try to do that with a complete process here. So let's say we have v1 is a vector, v2 is another vector, v3 is another vector, and they are all in the three-dimensional space, right? So R3 space in 3 dimensions. So, and you can also, start sketching these out, right? Like, for example, if you wanted to sketch 1, 2, and 3, so you have say three-dimensional space, x, y, and z. So in this case, you are going 1 on x, 2 on y, 3 on z, right? So 1 on x, 2 on y, 3 on z, and that particular point, like that vector, that is going to be your v1 vector, right? So 1 here, 2 here, 3 here. So that would be a vector in 3 dimensions. So that's your v1 vector. Then you have another v2 vector in 3-dimensional space, and you have another vector v3 in 3-dimensional space as well. The question here is, how do you check for linear independence? How do you check whether these vectors are linearly independent or not? Well, you start with the vector equation, which is k1 v1, k2 v2, k3 v3. Is that going to give us, are they going to be values, non-trivial values for k1, k2, k3 that actually you can use that as a linear combination of these 3 vectors to get a 0 vectors? So all we are requiring equivalently is k1 v1 plus k2 v2 plus k3 v3 should equal the 0 vector. Well, if you want to find those k1, k2, k3 values, then you'll have to turn them, as Sunny pointed out, into a set of equations. What are those set of equations? Well, let's try to see here. If you look at this, what is this? If you do a scalar multiplication of each vector with k1, with k2, with k3, you get k1, 2k1, 3k1, 0, k2, negative k2, and so on, right? You can do scalar multiplication, and then you can do matrix addition. And when you do that, you will get k1, nothing k for k2, and then 2k3. That will be your first row, first column entry. Next, second row, first column, it will be 2k1 plus k2 plus k3. And the last one will be 3k1 minus k2 plus 0, nothing there. So these should equal zeros, right? So this has to equal 0. That's giving you this equation. And then you have this guy equals this 0. So that gives you this equation. And then the last one, this guy gives you 0. So that gives you the third equation. So you've got 3 equations and 3 unknowns, and you're trying to find out whether are there any non-trivial solutions for k1, k2, k3, and if there are, then it is linearly dependent. If there are no non-trivial solutions, then it is linearly independent. So we are going back to solving a set of equations now. And so let's see. We are going to start with this guy. We have got something like ax equals 0 problem, right? It's like a homogeneous set of equations. All the right-hand side coefficients are 0. So it's a homogeneous set of equations similar to the ones that we have seen before, ax equals 0 problem. That's what we have here. So coefficients, unknowns, we call the coefficient matrix A, we call the vector of unknowns X. In this case, our coefficients are 1, 0, 2, and so on, and 2, 1, 1. All the unknowns X are k1, k3, and so on, k1, k2, k3. So let's try to solve them. So we have the same set of equations carried over from the previous slide, and we are trying to write the augmented matrix for this. So both the coefficient matrix and the right hand side constants. So of course the right hand side constant, this is a homogeneous set of equations, so the right hand side constants are going to be 0 anyway, and then you have got all those coefficients. Now I want you guys to notice each column in the augmented matrix that was formed. Each column in the augmented matrix is exactly the same as each vector that we were checking for, right? So each vector, like 1, 2, 3, that was v1, it became the first column of the augmented matrix. And then next one, 0, 1, -1, that was v2. And then similarly v3, let me use a different color for that. So all we did was, if you were given a set of vectors and you wanted to find whether they're linearly independent or not, you can jump to this step right away. You can start an augmented matrix which each of those vectors and then followed by a 0 vector because of the equations turning out to be homogeneous. Now from here we know the drill, the Gauss-Jordan elimination or Gauss elimination process to find the vector of unknowns. In this case, we are trying to find solution sets for k1, k2, k3. So you can do some row reductions here. This is, row 2 minus 2 times row 1, row 3 minus 3 times row 1. You have seen this process before. You end up with a, let's see, this is a echelon form, which we can try to, now we can use this echelon form to comment about the solutions, right? So this will give you what? This will give you, this one will give us k3 equals 0. And then you can use that to get, using this and this, we can say k2 minus 3k3 equals 0, which means k3 was 0, so k2 has to be 0. And then you can use that same thing to do it for this. So if you use this, you can say k1 plus 2k3 equals 0, which implies k1 is also 0, right? So what did you get? You got the only solution is the trivial solution here. k1, k2, k3 are all 0. So this would be a linearly independent set of vectors. So you see what we did? We took the vectors, we put them in an augmented matrix, and it's a homogeneous set of equations that we get. So we paired it with a vector of all zeros there for coefficient vector b. We did the row reductions, got it down to either a row reduced echelon form or echelon form in this case is sufficient. And then we started looking at the values of k that satisfy the equations. So the only set that was possible is the trivial set of equations for k1, k2, k3 to be 0, which makes the system of vectors, set of vectors, linearly independent. So that means that there are no, so k1 v1 plus k2 v2 plus k3 v3 equals 0. There's no other possibility for the given three vectors. There's no other possibility with which you can cancel these three out to get a 0 vector, except for when all the k's are equal to 0. That's what linearly independent set of vectors mean. Questions about this example? All right, let's continue. Now, we have another example here, but we have a linearly dependent example. So let's go through this very quickly. We have an augmented matrix here. Right? This is an augmented matrix. So we got one vector, the second vector, the third vector, right? We are trying to find out whether these vectors are linearly independent or not. So we've got these three vectors in R4 space. It's in a four-dimensional space. We have you get the homogeneous set of equations. So the last column is going to be a zero vector. We are going to start doing row reductions. The steps are given to you so that you can validate them. Eventually, you get this particular row reduced in echelon form. Reduced echelon form. So what can we say about this? Well, zeros, so that doesn't give me any useful information. But we get useful information from these two, right? So in this case, I'm using x1, x2, x3. We were using k1, k2, k3 before, right? So using this, you can say x2 or k2 plus 2x3 equals 0. And then from the first one, you can say x1 plus x3 equals 0. Clearly, for any value of x1 you pick, you will get x3 to be the negative of that. And so, right, you can say x1, if let x1 is t, some arbitrary value t, then you get x3 to be negative t, and you get x2 to be 2t, right? Is it 2t? Negative 2x3, negative cancels 2t, right? Or over here, I said x3 was t. I assumed x1 is t here. So what that means is you pick any arbitrary value for x3, you get their corresponding values for x1 and x3 for any t, right? T could be 1, 2, 3, any value. For example, if t is negative 1, what do you get for x1, x2, x3, right? So you get t is negative 1, which implies x1 is negative 1, x2 is 2t, so negative 2t, negative 2, and x3 is 1. So if you put that in our equation, k1 v1, k2 v2, and k3 v3, what do you get? x1 v1, so that's negative v1, negative 2 v2 plus v3 equals 0, or if you zero vector here, or if you multiply it out by negative 1, you get v1 plus 2v2 minus v3 equals 0, which is what we have over here. So we were essentially able to find out a non-trivial solution to our vector equation k1 v1, k2 v2, k3 v3, which makes it linearly dependent set of vectors. So we can say these three vectors over here are a linearly dependent set of vectors. Questions here? Okay. Now let's quickly summarize. So what we do first is we are putting the vectors as columns of a matrix A, right? So we've got all those columns v1, v2, v3, and so on up to vr. Those are columns. Then we solve the homogeneous system of equations ax equals 0. And we know where that 0 comes from because the vector equation has k1 v1, k2 v2, so on up to has to be 0. Right. So we start with the vector of equations. We'll put these columns we'll put these vectors as columns of matrix A, and then we'll solve the homogeneous system of equations, which is ax equals 0. And if x equals 0 is the only solution to this, then we call that set of vectors v1, v2, and so on up to vr a linearly independent set of vectors. Or if we have at least one non-trivial solution, then we call it a linearly dependent set of equations, dependent set of vectors v1, v2, and so on up to vr. So that's how we would check for linear independence. Take the vectors, put it in Ax equals 0, put it as columns of the matrix A, form the augmented matrix with the homogeneous set of equations will transform into a augmented matrix. Then you solve for the system. Check whether you get non-trivial solutions or not. Okay. Next, linearly dependent sets. We are focusing on linearly dependent sets. We are going to try to express one vector in terms of other vectors, right? So we are essentially trying to do something like this. So v1 can be written as negative 2v2 plus v3, right? So that is writing one vector in terms of other vectors as linear combination of other vectors. Let us see how we can do that. So expressing one vector in terms of others. So what the theorem is, if you have a set of vectors v1, v2, v3 and so on up to vr, and if it is linearly dependent, if one of the vectors can be expressed as a linear combination of the others. So if you are able to express these vectors as a linear combination of others, then we call it a linearly dependent set of vectors. And the key here is one, right? Only one has to satisfy. You don't have to do this for each of them. You only have to find out for one. If one of them you can do it, then you call it a linearly dependent set of vectors. Let's take a look at an example. We have three vectors here, v1, v2, v3. They are all in R4 space, four-dimensional space. We have seen this example before, where we have taken this, we have formed an augmented matrix whose columns were first column here, second column here, third column here, fourth column was all zeros, 4 zeros. Then we did the row reductions. Then we found out the values of k1, k2, k3. It turned out to be 1, 2, and -1 satisfied that equation. So if you rearrange this, what do you get? You get v1 equals -v2, 2v2 plus v3. You are able to express v1 as a linear combination of the other two vectors. And because you are able to do this, you call this a linearly dependent set of vectors. Next, let's take a look at an example which is slightly different. You have three vectors here, v1, v2, v3. These three vectors are in R3 space, a three-dimensional space. And let's try to take a look at v1 and v3, right? So if you take a look at v1 and v3, you can right away say, if you double v1 and multiply it by a negative sign, you get v3, right? So you see this from here to here. v3 equals negative 2 v1, right? So which is this guy right here. So you are able to express v3 as a linear combination of v1, in this case just v1. The coefficient of v2 is 0, but you are able to express v3 as a v1 using v1, which makes it a linearly dependent set of vectors. So linearly dependent. It has to only satisfy for one. To elaborate more, you can see that v2 is not a linear combination of v1 and v3, right? Because when you say v3 equals negative 2 v1, the coefficient of v2, k2, is a 0. So v2 you are not able to express in terms of v1 and v3, which is not a problem. You only had to satisfy for one, and you were able to do it for v1 and v3. Sure, you are fine. You have a linearly dependent set of vectors. So this one is only one of has to satisfy, not each of. So that's so to summarize, if you are able to express one vector in terms of other vectors, then you call it a linearly dependent set of vectors. You only have to satisfy for one. Don't need to check for more than that for dependence. Next, let's try to take a look at the zero vector and linear independence. So you have a set of vectors. Hold on, let's see if we can elaborate more on this. So here, let me add a slide here. Let's try to elaborate this with a general example. So what I'll do is I will pick S, my set of vectors, and I will call them V1, V2, and so on up to VR. Right? So let us say that this is linearly dependent set of vectors. Right? And I'm assuming that this is linearly dependent set of vectors, which means that there exists some k1, k2, and so on up to k sub r with that vector equation k1 v1 plus k2 v2 plus and so on up to kr vr equals 0 vector, right? So if we call this linearly dependent set of vectors, we know that there are some scalars that exist which satisfy the set of vectors, the vector equation. Now let's try to rearrange. So if you rearrange, what do you get? You get k1 v1. K1 v1 can be written as negative k2 v2 negative k so on up to k. So what you can say is this can be say I will use I going from 2 to r negative k sub I and v sub I. Can I say that? So I've essentially put all of these guys to the right hand side here, and I've written it as a summation. So now I needed v1, right? So what would be v1? This implies that v1 would be negative summation I equals 2 to r k sub I divided by k sub 1 vi, right? You guys see that? So this is what is this? This is expressing one of the vectors as a linear combination of the others, right? So we are not including I equals 1 here, because so all the others are being included over here. This is some scalar divided by k1, right? K sub I divided by k1. So this would be k2 by k1 or k3 by k1, so on up to kr by k1, right? So this is, let me write that. So v1 is a linear combination of v2, v3, so on up to vr. You see that? So we are able to express one vector as a linear combination of all the other vectors. So this is to say what? If you have a linearly dependent set of vectors, then you will be able to do this. You will be able to express one vector as a linear combination of the others. But the other question is, if you are able to express a vector as a linear combination of others, is it linearly dependent? Like the other way, is it true as well? Let's try to prove that right here. Sure. So we are going to start off with considering that some vector vj, v sub j, is a linear combination, can be expressed as a linear combination. All right, the linear combination of other vectors. Remember why we are doing this? Given linear dependence, we can be able to do this. Now the question is, if we know that one of the vectors can be expressed as a linear combination of others, is the set linearly dependent, right? Like going backwards. That's what we are checking. So if Vj is a linear combination of others, what can we say about negative Vj? Well, we were able to find V1, right? The same way we will be able to find Vj, V sub j, some jth vector. We can write this as negative summation I doesn't equal j k sub I divided by k sub j. All I'm doing is j instead of a 1. And I need to do a v sub I. This is for any general vector. We did for v1 earlier. What does this imply? This implies that if you bring vj to the right hand side, or you bring right, so if you have vj, one will be minus, one will be plus, right? So vj minus summation I doesn't equal j k sub I k sub j vi equals 0 vector, right? I've just rearranged that. Now let k sub j scalar be negative 1. If you pick k sub j to be negative 1, what do you get? Vj that is going to go to negative 1, right? So you get plus summation I not equal j ki divided by kj vi equals 0 vector. Kj is done. Right, kj is negative 1. I put that. Now you can bring in the vj as well in the summation, right? So vj, the coefficient is what, 1. So you can just bring that in to the summation here, making it summation for all ai equals 1 to r k sub I v sub I equals 0 vector. Which means what? Which means that linearly dependent set of vectors. So you guys see that? So if you start with the assumption that it is linearly dependent set of vectors, then you can do this. You can write any vector as a linear combination of the others, and you can do the other way as well. If any vector is a linear combination of the others, then we can also say that it belongs to a linearly dependent set of vectors. So one implies the other. All right, let's move on here. Let's consider the 0 vector and linear independence, right? So if suppose you have a set of vectors v1, v2, and so on up to vr, and it happens to include the 0 vector, right? Of all the r vectors, it has one of them, at least one of them, to be a 0 vector. Then immediately you can say that it is a linearly dependent set of vectors. You can say that. So let's try to see how we can prove this. Right, so you're saying that one of these is a 0 vector. If that is the case, it is linearly dependent set of vectors. So let's try to see. So what we can say is, for convenience, we'll pick v1 to be the 0 vector. And if that is the case, you have what? k1 v1 plus k2 v2 plus and so on up to kr vr equals 0. That's your vector equation. Then what do you have? We picked v1 to be a 0 vector, which means what? k1 0 plus k2 v2 plus and so on up to kr vr is going to equal 0, because we have put let v1, one of them, to be a 0 vector, which essentially says you can take anything for k1, right? you can take anything for k1, and you can make k2 equals k3 equals so on up to kr equals 0 and get a solution, right? So if you make k1 equals 5 and all the other k's are zeros, it will satisfy this particular equation, which happens to be a non-trivial solution. So we have a non-trivial solution, which is 1 followed by zeros, all zeros, or 2 followed by all zeros, anything followed by all zeros. That's your non-trivial solutions. So we can say that it is linearly dependent set of vectors. Right? So if any one of these vectors are going to include a zero vector, then that is going to be a linearly dependent set of vectors. We just assumed v1 to be that zero vector, and we were able to satisfy this. And you can do that same thing for any v2, v3, vj, anyone. Next, let's take a look at unit vectors. Unit vectors are sort of vectors or columns of identity matrix. So unit vectors e1, e2, e3, so on up to en in n-dimensional space, in Rn space, are vectors which only have one entry as 1. For e1, it is 1 here, e2, second one, en, 1 here. So these are all unit vectors in n-dimensional space. They are all linearly independent, and it is easy to see this. No matter what you do, you will never be able to make a linear combination of these go to a 0, because you will never be able to manipulate this one with bunch of zeros, this one with a bunch of zeros. So no matter what you do in terms of your linear combination, you will never be able to get eventually a vector of all zeros, which makes this a linearly independent set. The only solution will be your trivial solution. So these are your unit vectors. Next, more vectors than dimensions. So in this case, we have a set of vectors v1, v2, and so on up to vr. So we have r vectors. Each of these vectors is in n-dimensional space, so Rn space, right? So essentially that means that each of these vectors, right? So you can say this, v1 will be a vector which has what I can say this has n rows, right? So each of these will have n rows. So number of vectors are r, number of rows in each vector is n, and we are assuming that we have more vectors than dimensions, so r is more than n, right? So number of vectors we have is more than n, and if we have r to be strictly greater than n, then we can say that we have a linearly dependent set of vectors. Now this particular statement doesn't go backwards. We cannot say that if we have a linearly dependent set of vectors, then r is greater than n. We cannot say that. We have clearly seen some examples earlier where that was not true. But if r is greater than n, then we can say that it is linearly dependent set of equations. We can say that because we get a homogeneous system of equations for ax equals 0 solution. We get a homogeneous system with more variables than unknowns, than the constraints, which makes it have many solutions, and we can say that it is linearly dependent because of that, because we have non-trivial solutions now. So we can start off with, say, A to be v1, v2, and so on up to vr. These are all vectors. They are r vectors, right? And there are n rows in each vector. So what would happen when you do ax equals 0, or x is x1, x2, x3, we are using k1, k2, k3. What are you going to have? Well, this is going to have a rectangular matrix, not a square matrix, right? Because A has more columns than rows. And then you are doing this with the number of columns here, which is R, has to match up the number of rows here, equals that vector 0, right? So this is going to be a 0 vector here. But you can see that when you have this particular situation where we have more rows than the constraints, it is the same as translating that equations in k1, k2, k3 to be more variables than the constraints. So essentially, if you look at this particular example here, right, we had k1, k2, k3, we had 3 equations and 3 unknowns. Now, if you start putting in more and more R, right, so we had 3 of them. If you have 4 of them or 5 of them and so on, the constraints are only 3, or if you have R to be greater than N, so in this case we had R equals N, right? So R is the number of vectors. So in this case we had 3 vectors. What if we had 4 vectors? If you had 4 vectors, you would get k1, k2, k3, k4. But you only have 3 equations in that case, because the number of rows here indicate the number of equations that you get. So if you have 4 unknowns and in k1, k2, k3, k4 and only 3 equations, then you know that that is going to lead to, if there is a solution, if the system is consistent, you know it's going to have infinitely many solutions, which means that it has non-trivial solutions. In other words, it's going to be linearly dependent set of vectors. So because of the sizes, we can say that. All right, so let's take a look at some linear dependence, but we'll look at it geometrically. So over here, I'm sketching vectors in 2-dimensional space, right? So each of these vectors, I'm assuming that it has each vector has 2 entries, right? So maybe this is what v1 is, something like 1 and 1, right? So it's going up 1 and 1, and then v2 maybe is going over here 2 and 2, right? So if those vectors, when you sketch them out in 2-dimensional space or n-dimensional space, if they are collinear, they are on that same line, they are collinear, then these are linearly dependent. So you can clearly see, if you take v1 and multiply by 2, you get v2, right? So you can say something like this, v2 equals 2v1, right? And we know that if you are able to express a vector as a linear combination of others, it's a linearly dependent set of vectors. We proved this earlier. And similarly, over here, what do we have? We have something like this, right? So maybe this is -1, -1 vector, and then this is the same 2, 2 vector. So in this case, they are still linearly dependent. So this is linearly dependent. Why? Because now again we can do the same thing. I can write v2 vector as -2 times v1 vector, right? So it's the same line, but they're pointing in opposite directions. But still, there is a way to express one vector as a linear combination of the other. In this case, there's no combination, just a factor of the other. So it's still linearly dependent. But if you have something like this, you see v1 and v2, then they are linearly independent if they are not collinear. So let me write this over here, linearly independent. So you cannot express v1 as a factor of v2 in this case. So maybe it is going something like on x it is going maybe 1, on y it is going 3, but over here it is going for v2 maybe it is going 2, 2, right? So you can never do anything to v1 to get something for v2. You can never do that. What does the line under the vectors signify? That it is a vector. So earlier, when I typed things out, I was able to make this bold, right? So when I make it bold, I'm able to identify vectors. But, I don't want to do something like this. I don't want to keep changing my width of my line. I don't want to write V1 like that. So if I want to use a thin line, a normal line, then I'm using V1. So it's just indicating it's a vector. All right. Let's see. So, you have something. So here you see this particular equation, K1, V1, K2, K. So K, V1, V2, VR, 0, these are all vectors. K1, K2, K3, these are all scalars. All right, let's see here. Okay, so dependent, dependent, independent. Three vectors are linearly dependent if and only if they lie in the same plane. So if you have three vectors and if you want them to be linearly dependent, it is possible in 3 dimensions if they all lie in the same plane. Next, non-singular matrices. So for non-singular matrices, these are square matrices, right? You see this is n by n. So this means that we are talking about square matrices here. The definition of a non-singular matrix is a square matrix with only one, if the only solution to Ax equals 0 is the trivial solution. Right. So if you get the trivial solution, so that means that the vectors in the non-singular matrix are linearly independent, right? So if the vectors in the non-singular square matrix are linearly independent, then this will be the case. Ax equals 0 problem will only have a trivial solution, right? So you can say linearly independent set of vectors. Square matrix for which the only solution is the trivial solution. Next, if a matrix is not non-singular, then it is singular. That means that it is going to have vectors that are linearly dependent. Let us say that your A matrix has a bunch of vectors, A1, A2, A3, so on up to AN. It has n vectors. Then the homogeneous system that you're going to try to solve is Ax equals 0. You can write that as x1 a1, x2 a2, and so on up to xn an. We were writing k1 v1. Now you are writing x1 a1. To go back to that ax equals b or ax equals 0 problem. So bold A's are corresponding to the columns in the coefficient matrix A. X is your vector of unknowns, x1, x2, x3, s1 up to xn. And then on the right hand side, you have a 0 vector. So we have the following theorem. An n by n matrix A is non-singular if and only if the set of vectors A1 through AN is a linearly independent set of vectors, right? So linearly independent set of vectors means x equals 0 is the only solution, the trivial solution. So if it is a trivial solution, that's the only solution that is possible, then you can say that it belongs to the square matrix, which is non-singular. Let's take a look at an example of singular and non-singular matrix over here. This particular matrix, the claim is that it is non-singular. First of all, it is a square matrix, so that checks out. And then if you look at the columns of this matrix, they happen to be linearly independent. How do we know this? Well, because we have seen that the augmented matrix of this reduces to this earlier, right? So if I go back to a little bit ago, give me a second here, right? So that was the square matrix that we were looking at. When you form Ax equals 0, then you get this, row reduced to this. When you row reduced and look at the solutions, you get the trivial solution. So if that is the only solution that is possible, then it is linearly independent set. So the square matrix that we started off with is going to be a non-singular matrix. So start off with the square matrix, form the homogeneous system of equations Ax equals 0, do the row reduced form, find the values of k1, k2, or in this case Ax, right? So x1, x2, x3, and so on. And if x equals 0 is the only solution, the trivial solution, then you can say that the square matrix that you started off with is non-singular. However, consider this matrix here. This matrix over here is a square matrix. And if you took this matrix and formed the augmented matrix 1, 2, 5, 0, 0, 5, 10, 0, negative 3, 1, negative 1, 0, did the row reduction, the row reduction will take you here. Row reduced. So row reduced form takes you here, and from here what we can say is, let's see, if I look at this, I can say x2 plus 2x3 equals 0, and from here I can say x1 plus x3 equals 0, and clearly I can pick arbitrary values, right? I've got 2 equations and 3 unknowns, so I'm going to have infinitely many solutions here, because as long as they are consistent. So I can pick, say, x1 equals t. That will imply that x3 equals negative t, and that implies that x2 is going to be negative 2x3, which is going to equal 2t, right? So for any value of t, for example 1, if you pick t to be a 1, you got a 1 there, and you got a negative 1 there, and you got a 2 there. So you got a lot of non-trivial solutions, right? Non-trivial solutions. So essentially we are saying that Ax equals 0 does not have only one trivial solution. It has many non-trivial solutions, which makes it singular. All right, questions about this? All right, let's see. That's all I have for you guys today. I'm going to stop recording. I will see you guys on Friday. Remember, homework 6 is due tonight. What else do I want to say? I want to say, yeah, the next time we meet, we'll start looking at matrix inverse. We'll focus on non-singular matrices. So that's what we'll do when we come back. All right, I will see you guys on Friday.